it looks like they detected the interstellar visitor, 3I Atlas, that was discovered back on July 1st, 2025, this year.
The moment felt like a turning point in our exploration of the cosmos. On August 6, 2025, the James Webb Space Telescope accomplished what seemed impossible, capturing the first true infrared portrait of 3I/ATLAS, an ancient wanderer from another star system, revealing secrets that challenge everything we thought we knew about comets. From the first glimmer of planning, astronomers knew that 3I/ATLAS was special. Discovered in early July 2025 by the Atlas Survey System, it was identified as only the third confirmed interstellar object ever detected. The preceding two, Oumuamua and 2I/Borisov, had already expanded our understanding of what might cross into our solar system, but both carried caveats and mysteries. Oumuamua defied simple classification, its tumbling motion and strange acceleration puzzling scientists to this day. Borisov, while comet-like, still left open many questions about chemistry and origin. Now 3I/ATLAS was on a path that would bring it deeper into our observational reach, and waiting to catch it in the act became a bold gamble against time and chance. This wasn't just another space rock passing through our neighborhood. It was a messenger from the depths of interstellar space, potentially billions of years old, carrying information encoded in its ices and dust about a stellar system we may never directly observe. The significance cannot be overstated. Each interstellar visitor is a piece of the galaxy's story, delivered directly to our doorstep. With only 3 such objects ever confirmed in human history, every observation becomes precious, every data point irreplaceable. The discovery sparked immediate excitement across the astronomical community, with observatories worldwide scrambling to coordinate viewing schedules before this rare visitor slipped away forever. What makes interstellar objects so valuable is their ability to serve as time capsules from other star systems. They carry chemical signatures, structural features, and physical properties shaped by environments completely different from our sun's influence. By studying them, we gain windows into planetary formation processes occurring light years away, under conditions we can only theoretically model. 3I/ATLAS represents an unprecedented opportunity to test our theories about how comets form, evolve, and survive in the hostile environment of interstellar space across cosmic timescales. The James Webb Space Telescope managed to lock onto 3I/ATLAS using its near-infrared spectrograph, NIRSPEC. That single pointing was the culmination of delicate calculations and precise trajectory modeling. Because from that vast distance, the comet is a faint moving target against a shifting backdrop of stars. The team had to ensure the comet would fall within Webb's narrow field of view, even as it hurtled inward toward the sun at extraordinary speeds exceeding 130,000 miles per hour, roughly 210,000 kilometers per hour. Success meant not just an image, but a spectral map of the comet's glowing shroud, the coma that surrounds its nucleus. That achievement alone felt like threading a needle across astronomical distances. Consider the variables involved in this cosmic ballet. The comet's velocity meant its position changed dramatically between the time observations were planned and when they were executed. Webb's orbital position at Lagrange Point 2, about 1 million miles from Earth, added another layer of complexity. The time delay in communications, the telescope's pointing limitations, and the need to predict exactly where this interstellar traveler would be days or weeks in advance all compounded the challenge. One miscalculation, one slight error in trajectory prediction, and the observation window would close forever. The comet moved so fast that traditional observation techniques had to be adapted specifically for this target. Webb's operators developed new tracking algorithms, tested backup pointing strategies, and coordinated with ground-based telescopes to refine position measurements up to the last possible moment before the observation sequence began. The narrow field of view that makes Webb so powerful for detailed observations became a liability when trying to capture a rapidly moving object. It's like trying to photograph a speeding bullet with a telephoto lens. Possible, but requiring perfect timing and prediction. This technical triumph demonstrates not just Webb's capabilities, but the ingenuity of the teams operating it. The image that emerged was unlike any simple snapshot of a comet. It revealed a dense carbon dioxide-dominated coma, radiating in infrared wavelengths between 0.6 and 5.3 micrometers. Within that glow, signatures of water vapor, carbon monoxide, water ice, dust, and trace molecules such as OCS, carbonyl sulfide, were faint but present. but the dominance of CO2 was the standout feature that stunned researchers. There was roughly 8 times more CO2 in the coma than water vapor, a ratio among the highest ever recorded in any comet, interstellar or otherwise. That fact alone forced a rethinking of how this object formed and evolved. To see a comet so heavily skewed toward carbon dioxide outgassing is to stumble upon a relic unlike the ones we know in our own solar system. In typical comets, as they approach the sun, sublimation of water ice dominates the show. Water vapor drives most of the activity, and dust is lofted outward, creating visible tails and halos of particulate matter that can stretch for millions of miles. But in 3I/ATLAS, the relatively weak water signal hints at something fundamentally different, perhaps a crust of insulating material preventing heat penetration, or an internal structure that retards warming in unexpected ways. As a consequence, the water-rich layers might remain frozen deep within, while CO2 and CO volatiles, which sublimate at much lower temperatures or require less energy to vaporize, are the ones driving the visible activity we observe. This chemical fingerprint likely echoes conditions in a different stellar nursery altogether, one where carbon dioxide played a more dominant role than in our sun's protoplanetary disk. The balance of dust, gas, and ice in that coma becomes a fingerprint of the comet's history, encoding information about temperature gradients, pressure conditions, and chemical abundances in its birth system. Beyond the chemistry, the structure of the coma in Webb's images offers subtle clues that specialists are only beginning to unravel. The enhancements in the sunward direction suggest that outgassing is stronger on the side facing the sun. No surprise in itself, but the degree to which that directionality appears and how steep the gradient of gas emission is can disclose crucial information about the surface geometry and perhaps even the rotation of the nucleus. The dominance of gas emissions over large expanses implies that the comet is shedding material across broad zones, not just from isolated vents or active regions as we see in many solar system comets. In many ways, the shape and brightness of those emissions encode a silent map of internal pressures, fractures, and the thermal insulation the comet has accumulated over millennia of exposure to the harsh interstellar environment. Spatial gradients in emission hint at extended outgassing zones rather than narrow jet sources. The gas appears to emanate broadly from sunward-facing regions, but also with less abrupt fall-off than pure surface spot models would predict. That distribution pattern suggests subsurface conduction pathways, extensive fracture networks, or layered sublimation zones that tap into volatile reservoirs located well below the immediate surface skin. The radial brightness profile, when mathematically deprojected to account for viewing geometry, can yield a column density map of gas distribution. This in turn constrains gas velocity fields and diffusion coefficients, critical parameters for understanding the comet's internal physics, porosity, and how efficiently heat conducts through its structure. Meanwhile, the motion of dust particles against the backdrop of gas provides additional clues. Dust becomes entrained in gas flow but can lag behind or decouple entirely if grains grow too large or if gas drag forces weaken with distance from the nucleus. Yet Webb's observation is more than a chemical inventory, more than just an image of a distant wanderer passing through our cosmic neighborhood. It is a bridge between our solar system and the unknown realms this object passed through during its long journey, connecting the physics of formation in distant protoplanetary disks with the processes we observe in our own backyard. If 3I/ATLAS indeed formed near a CO, 2 ice line in its parent system, the environment around its natal star must have differed drastically from the conditions around our young sun billions of years ago. That helps place powerful constraints on how disks of gas and dust evolve around different types of stars, on how volatiles freeze out and migrate through these disks, and on how planetesimals assemble under varying irradiation regimes and temperature profiles. We now hold direct observational data, not theoretical conjecture, from a comet that has traveled light years across interstellar space to deliver a message about distant star systems. The implications ripple through multiple fields of astrophysics simultaneously. Planetary scientists gain valuable insights into disk chemistry around other stars, particularly regarding how carbon-rich versus water-rich regions form and evolve. Cosmochemists receive precious new data points about volatile distributions in different stellar environments, helping calibrate models of chemical evolution. Astrobiologists must now consider how organic chemistry might develop in systems with different ice compositions and volatile ratios. Some estimates based on velocity and trajectory analysis place 3I/ATLAS ATLAS's origin in a region of the Milky Way's thick disk, implying it could be between 3 and 11 billion years old, potentially far older than our 4.6 billion-year-old solar system itself. If correct, this comet may have drifted through the galaxy for eons. The physical dimensions of 3I/ATLAS themselves demand careful attention and reveal intriguing puzzles. Based on observations made through August 2025, the upper limit on its diameter is estimated at about 3.5 to 5.6 kilometers, though it may be as small as roughly 1.4 kilometers across. This significant uncertainty in size determination is not a trivial matter or mere observational limitation. For a body actively shedding gas and dust, radius matters enormously for determining how much surface area is available for outgassing, how deep thermal waves can penetrate into the interior, and how internal heat conduction might govern ongoing activity patterns. A larger, more massive nucleus could resist the recoil forces from outgassing jets, which might explain one of the most perplexing aspects of 3I/ATLAS. It exhibits almost no measurable non-gravitational acceleration despite clear signs of substantial gas emission. In typical comets, the recoil from jets of evaporating gases acts like tiny rocket engines, slightly altering the object's orbital motion in measurable ways. But 3I/ATLAS appears sufficiently massive or structurally rigid that those forces fail to perturb its trajectory detectably. That apparent inertia suggests extraordinary bulk density, unusual internal cohesion, or perhaps a shell-like structure that somehow suppresses asymmetric thrust effects. Some analyses have placed its total mass at over 33 billion metric tons. Though these estimates carry large uncertainties due to the difficulty of measuring such parameters remotely, the mass-to-size relationship becomes critical for understanding the comet's evolution and behavior. A nucleus toward the larger end of size estimates, several kilometers in diameter, would carry sufficient inertia to resist outgassing perturbations easily. Conversely, a smaller body loaded with internal porosity or extensive fracture networks might be more easily nudged by jet forces, yet we see no such effect. What makes 3I/ATLAS stranger still is how early it became active compared to typical cometary behavior patterns we observe in our solar system. The observational campaign surrounding 3I/ATLAS represents one of the most coordinated multi-wavelength efforts in recent astronomical history. While Webb's infrared spectroscopy provided the crucial chemical breakthrough that grabbed headlines, it was far from working alone in unraveling this comet's mysteries. The Hubble Space Telescope captured detailed visible light images on July 21, 2025, when the comet was approximately 277 million miles from Earth. Its images revealed a distinctive teardrop shape in the dust cocoon surrounding the nucleus, providing essential constraints on dust particle anisotropy, mass loss rates, and the geometric structure of the developing tail. Ground-based observatories have also played indispensable roles. The Gemini South and Gemini North telescopes have been tracking the changing tail structure and monitoring its growth as the comet steadily nears the Sun. The Neil Gehrels Swift Observatory contributed crucial ultraviolet observations that identified emission from hydroxyl OH radicals, which serve as reliable tracers of water sublimation processes. These observations yielded an inferred water production rate of approximately 1.35 times 10 to the 27th molecules per second, translating to roughly 40 kilograms of water vapor escaping every second when the comet was about 3.5 astronomical units from the Sun. The Transiting Exoplanet Survey Satellite, TESS, provided an unexpected contribution through pre-recovery observations. Astronomers found the comet lurking in archived images taken before its official discovery date. This archival mining allowed them to backdate the comet's activation threshold and track its brightening curve over a longer baseline. Polarimetric studies added yet another dimension to our understanding. Measurements of how scattered sunlight becomes preferentially aligned revealed that 3I/ATLAS exhibits an unusually deep and narrow negative polarization branch, a combination rarely seen among both asteroids and comets within our solar system. This unique polarization signature suggests the dust grains have distinctive scattering properties, possibly indicating unusual sizes, surface textures, or high porosity levels. As 3I/ATLAS approaches its moment of greatest transformation in late October 2025, astronomers face an ironic and deeply frustrating reality. Just when this interstellar wanderer should reveal its most spectacular secrets, just when solar heating reaches its maximum intensity and drives the comet into its most active state, Earth's view becomes completely obscured. The comet's trajectory carries it directly behind the sun from our perspective, creating an observational blackout during precisely the phase that promises the most dramatic changes. This cosmic timing couldn't be worse for scientists who have invested months coordinating observations and analyzing every scrap of data from this rare visitor. Terrestrial observatories, no matter how powerful or sophisticated, cannot peer through the sun's overwhelming glare. Even space-based platforms orbiting Earth share our blocked vantage point. The hidden window, stretching across days or potentially weeks, may witness explosive bursts of intensified outgassing as fresh, volatile ices suddenly vaporize under intense solar radiation. Nucleus fragmentation becomes a real possibility. The structural stresses from rapid heating and internal pressure buildups could literally tear sections of the comet apart. New volatile layers buried beneath protective crusts for billions of years might suddenly breach the surface, releasing chemical species never before detected in this object. Without continuous direct monitoring during these critical days, researchers must employ creative alternatives that feel frustratingly incomplete. Spacecraft positioned at different locations in the solar system might catch oblique views if their orbits happen to provide favorable geometry. Solar observing satellites like the Solar and Heliospheric Observatory or Parker Solar Probe, designed to study the sun itself, might capture peripheral glimpses of the comet as it skirts through their fields of view. Some ground-based telescopes at specific latitudes might achieve brief opportunistic sightings during twilight hours when the comet emerges momentarily from the solar glare at dawn or dusk. But these fragmentary observations cannot match the continuous monitoring coverage that astronomers desperately want. The analogy to theater feels apt. Imagine watching a suspenseful mystery play where the detective finally confronts the villain to reveal the truth. But just as the confrontation begins, the actor steps behind a curtain for the entire climactic scene. You hear muffled sounds, you see shadows moving, but the crucial visual details remain hidden. Only afterward, when the actor reappears, can you assess what happened based on the aftermath. That's essentially the situation astronomers face with 3I/ATLAS during perihelion. The comet will reach its closest solar approach at a distance roughly equivalent to Mars's orbit, about 1.5 astronomical units from the Sun. At this distance, solar radiation intensity increases dramatically compared to the 3.3 astronomical units where Webb captured its observations. The increased heating doesn't just warm the surface, it penetrates deeper into the porous nucleus structure, reaching volatile ices that have remained stable and frozen during the comet's inbound journey. Different ice species have different sublimation thresholds. Water ice requires more energy than carbon monoxide or carbon dioxide, while exotic ices like ammonia or methane have their own distinct temperature requirements. As the comet heats up behind the Sun, these thresholds get crossed in sequence, potentially creating layered outbursts as each volatile species reaches its vaporization point. The gravitational slingshot effect during perihelion passage will then fling 3I/ATLAS back outward on its hyperbolic escape trajectory, accelerating it to speeds that will eventually carry it completely out of our solar system. This visitor will never return. Its perihelion passage represents a singular, unrepeatable opportunity to observe how an interstellar comet responds to maximum solar heating, an opportunity largely hidden from our instruments. The tantalizing scientific questions during this blind period multiply with each consideration. Water vapor production might suddenly spike dramatically as thermal waves finally penetrate to deeper, water-rich layers that the initial CO2-dominated crust protected. The current 8-to-1 ratio of carbon dioxide to water could shift drastically, potentially even inverting, if massive water ice reservoirs begin sublimating. Silicate dust grains heated to hundreds of degrees might begin releasing adsorbed gases or undergoing thermal decomposition that produces entirely new gas species, perhaps sodium, potassium, or other metallic atoms that create distinctive emission lines. Organic molecules represent another frontier of possibility. Complex carbon-bearing compounds preserved in deep freeze for billions of years might suddenly vaporize and become detectable in the coma. Nitrogen-bearing molecules like ammonia, hydrogen cyanide, or more complex nitriles could flicker into existence in spectroscopic observations. These organic species would provide crucial insights into the prebiotic chemistry of the comet's birth system and how organic complexity develops in different stellar environments. But will these molecules appear during the hidden perihelion passage, only to fade again before Earth-based observations resume? The structural integrity of the nucleus itself hangs in question. Comets experiencing sudden, intense heating sometimes undergo catastrophic fragmentation. The nucleus literally breaks apart into multiple pieces. We've witnessed this drama before with solar system comets like Shoemaker-Levy 9, which fragmented spectacularly before impacting Jupiter, or Comet Linear, which disintegrated as it approached the Sun. If 3 I/ATLAS fragments during its hidden passage, we'll only discover this after the fact when the comet reemerges and observers notice multiple condensations or an abnormal coma structure indicating nucleus breakup. Alternatively, more localized collapse events might occur, sections of the surface crust giving way under pressure from sublimating ices beneath, creating sudden outgassing vents or exposing fresh volatile-rich material. These events can trigger brightness surges visible even at great distances, but if they happen behind the Sun, we'll miss the initial outburst and only see the gradually fading aftermath. The thermal and mechanical stresses during maximum heating could also activate dormant fracture systems, opening new pathways for gas escape that alter the comet's activity patterns when it becomes observable again. Yet despite these frustrations, the Webb observation captured in early August becomes even more precious as a benchmark. That detailed infrared snapshot showing the CO2-dominated coma, the molecular inventory, the spatial distribution of emissions, provides an essential before picture. When observations resume after perihelion passage and the comet swings back into observable sky, astronomers can compare the new state against Webb's baseline. Any changes in chemistry, activity levels, coma structure, or tail morphology will stand out clearly against that reference point. If the water to CO2 ratio shifts, we'll know the thermal evolution penetrated to different compositional layers. If new molecules appear, we can infer they originated from deeper volatile reservoirs accessed only during maximum heating. If the nucleus shows signs of fragmentation or the coma displays unusual asymmetries, we can deduce that structural changes occurred during the hidden phase. Webb's image transforms from just a snapshot into a crucial temporal anchor point that enables before and after comparison despite the observational gap. This success with 3 I/ATLAS fundamentally demonstrates that Webb has revolutionized our capability to study interstellar visitors. Previous interstellar objects like Oumuamua and 2I/Borisov challenged our observational capabilities. They were discovered relatively late in their solar system passages, limiting observation time, and our instruments struggled to extract detailed compositional information. Webb changes that equation entirely. Its infrared sensitivity reveals molecular fingerprints invisible to optical telescopes. Its spectroscopic resolution distinguishes individual chemical species that would blur together in lower quality data. Its spatial resolution maps emission patterns across the coma, revealing activity distributions and dynamic structures. Ground-based observatories, despite advances in optics and detectors, face limits imposed by Earth itself. The atmosphere absorbs key infrared wavelengths, blocks certain molecules entirely, and adds thermal noise that drowns faint signals. Even with adaptive optics, turbulence restricts resolution, while light and zodiacal glow obscure faint targets. These are physical, not engineering barriers. Even Hubble, above the atmosphere, struggles in the infrared due to its warmer temperature and limited instruments. The James Webb Space Telescope, positioned 1 million miles away at L2 and chilled to cryogenic levels, eliminates these issues. Its ultra-sensitive infrared detectors can isolate the faintest signals from distant interstellar objects, transforming quick sightings into deep, sustained scientific investigations of material from other star systems. Webb's image of 3 I/ATLAS opened a door into uncharted territory, transforming interstellar visitors from mysteries into subjects of rigorous scientific inquiry. As this ancient traveler speeds back into the cosmic void, it leaves behind invaluable data and profound questions, reminding us that the universe still holds countless secrets waiting to be revealed.